Let us consider the operation of one type of direct current motor, shown in this figure here. The centre part A is the armature or rotor. It is a cylinder of soft steel mounted on a shaft so that it can rotate about its axis. So it's going to rotate about this axis here. Embedded in slots in the rotor surface parallel to its axis are insulated copper conductors C. Current is led into and out of these conductors through graphite brushes making contact with a cylinder of the shaft called a commutator, which is not shown here. The commutator is an automatic switching arrangement that maintains the currents in the conductors in the direction shown, whatever the position of the rotor. So as this rotor spins, whatever conductors are here, 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 and here, and here, will always have the current moving in this direction, coming out of the page, if you like. And those around here will always have current going through them in this direction, going into the page. The current in the field coils, F and F, sets up a magnetic field. This here, you can see A and B, these here, this is one coil of wire and it's wound all the way around here. There's a magnetic field produced which goes in this direction here, and it goes in this direction here. So that's produced by these coils. So there's current going through these coils which produce the magnetic field. That current is a fixed current all the way through, so you're given this fixed magnetic field through this casing of the motor, if you like. The magnetic field lines are pretty much uniform going this way. With direction of field and rotor current shown, the side thrust on each conductor in the rotor is such as to produce a counterclockwise torque on the rotor. The magnetic field's going that way, and you know that if you rotate the I into the B, then you're going like that, so you're coming out. So the force is going up. So you can see that I've got an arrow here. That means that that's being forced to spin that way. And on the other side, it's the opposite, because obviously now the current's going in this way. So you can see here I've drawn the current going in here. Magnetic field going around. So in this case, the I is moving into the B. So the I is moving into the B like that. Therefore, it's going in that direction. So here, it's always, this part is always being pushed in this direction, and this part is always being pushed in that direction. These wires coming in and out, they might actually be connected in series with these wires using the appropriate commutator. They'll swap over, but they can always be connected in series. A motor converts electrical energy to mechanical energy or work, and this requires electrical energy input. The power input is going to be whatever the current we pass through here, whatever the voltage is on this this source of voltage. So that power input will be VAB, the measured potential difference between these, times whatever the current is that flows through them. Even if the motor coils have negligible resistance, there must be a potential difference between the terminals if P is to be different from 0. So you have to have some resistance in here for there to be a potential difference. This potential difference results principally from magnetic forces exerted on the charges in the conductors of the rotor as they rotate through the magnetic field. These forces are an example of non-electrostatic forces. The resulting electromagnetic force is called an induced electromotive force, or sometimes a back EMF, referring to the fact that its sense is opposite to that of the current. Induced EMFs resulting from motion of conductors in magnetic fields will be considered later on. So let's assume that this is wired up in series. Having internal resistance R, VAB is greater than E, the EMF, and the difference is the drop I times R across the internal resistance. Thus, for either a motor or a battery being charged, we have this relationship here. We have the voltage of the source equals the back EMF plus whatever voltage is being dropped across the internal resistance. Because of the nature of the magnetic field force, the EMF E is not constant but depends on the speed of rotation of the rotor. The behaviour of a DC motor is analogous to that of a battery being charged. In that case, electrical energy is converted to chemical rather than mechanical energy. So this sheet just goes through all the points I've made here. The centre part A is the armature, so that's the armature. The embedded slots are the copper conductors, so inside all of these embedded slots are the copper wires. F and F are the field coils, so these are the field coils. The gap between P and P carries a uniform, so you can see we've got a uniform magnetic field going through here. As the magnetic field goes right through the frame here. The power input, so the power that we produce from this voltage source delivered to A and B, is P VAB times the current that flows, and of course that has to equal voltage drop across the internal resistance plus the back EMF, the magnetic forces that are produced when this spins round. R is the internal resistance, E is the induced or back EMF. Its value depends on the speed of rotation of the rotor. VAB is always greater than the back EMF. The difference is the drop IR across the internal resistance. And finally, just repeat, behaviour is analogous to that of a battery being charged. In that case, electrical energy is converted to chemical rather than mechanical. So let's have a look at a quick example of that. A DC motor with its rotor and field coils connected in series has an internal resistance of 2 ohms. When running at full load on a 120 volt line, it draws a current of 4 amps. What is the EMF in the rotor? Well, we can use the fact that the voltage at the source is equal to the back EMF plus the voltage that's dropped across the internal resistance, IR. So we just plug in the values. 120 volts equals the back EMF, add 4 amps times 2 ohms, and we can then just rearrange that and find that the back EMF is 112 volts. So what is the power delivered to the motor? Well, the power delivered to the motor is the actual voltage from the source, which is 120 volts, times 4 amps. So the actual power delivered is 480 watts. What is the rate of dissipation of energy in the resistance of the motor? Well, we can get that simply by using the relationship I squared R. We know that the power there that is wasted, if you like, across the resistor, I squared R, 4 squared, 16 times 2, it's 32 watts. So that's how much power is wasted. And what is the mechanical power developed? Well, the mechanical power output is the electrical power input minus the rate of dissipation. So this is being dissipated, so it's just basically 480 watts minus 32 watts. So we end up with the mechanical power output is 448 watts. So we get from 480 to 448 watts. So that's the input power, and that's the actual resultant mechanical output power.